So in terms of remedial measures then to counter multicollinearity, one possibility is to try to use prior information about some parameters. Now this is discussed, albeit not very well, in Gujarati and Porter. That's why I sort of say here that textbooks often give some fairly extreme examples to illustrate this. Okay, I think these are primarily of theoretical rather than practical importance in terms of how these are discussed. So incorporating prior information about parameters sensibly would require more advanced Bayesian statistical methods, so there is real value in this. Okay, but this does lie far outside the scope of this course. Okay, so what I want to emphasize here is that this is something that's often given lip service by textbooks and often very unconvincingly, but there is real mileage in these sorts of Bayesian approaches. And what you're really trying to do with these methods that incorporate prior information, what you're trying to do is design a computational algorithm or recipe that will do the model selection for you with minimal analyst bias. Okay, so in some senses, what this actually entails is a sort of more advanced version of the stepwise regression methods that we'll talk about towards the end of this lecture. Okay, so there is real mileage in these sorts of Bayesian approaches, but we can't really do it justice. So alongside that, one of the key remedies to the problem of multicollinearity is to drop variables. So as it says there, the simplest approach to resolving multicollinearity is to drop one or more of the collinear variables. So for instance, if you look back at the slightly artificial lecture example, you could exclude wealth from the model. Now, it really depends on whether you're coming at this from a sort of economic theory perspective or just a pragmatic statistical modelling perspective. Some economists might express concerns about specification bias if variables identified by economic theory are not included in the model. And whilst this may be a valid concern, it does depend to some extent how much trust you want to place upon economic theory. Okay, and in my experience, I think this just depends on whether you've been taught initially by a bunch of economists or a bunch of statisticians. Now, probably the most practical way of doing this is to use stepwise regression or some similar more advanced techniques related to computer science to choose a model automatically according to an algorithm or numerical recipe, and there's a sense in which this might provide an objective approach to messy problems. Okay, so nothing is sort of completely objective, but the idea is that if you rely on some computational algorithm, you can hopefully avoid much of the analyst bias. So an alternative remedy to multicollinearity is to transform variables. So this might be possible in various different ways. The classic example for accounting and finance data is if you have time series data, you might consider forming a new model by taking the first differences, and it's thought that this approach can reduce the problem of multicollinearity. So just to emphasize here that whenever you've got data in the form of financial or economic time series, it's very common that you might take first differences, and this is indeed the standard approach for financial time series modeling, and we'll go through this towards the end of the course. Okay, so this might sound a bit strange when you first see this, but there is a whole branch of academic inquiry precisely based on these sorts of time series models where you take first differences. Beyond that, I think you're liable to see some of the textbook examples with fairly extreme illustrations of this, which will primarily be of theoretical rather than practical importance, but the way this certainly manifests itself in practice and in a meaningful sense is when you look at time series models and take the first differences. An alternative remedy is just to simply acquire new data. So the basic idea is that if you acquire additional data or a new augmented sample, then the data set that you get from that will be much better. And remember that multicollinearity is a sample feature, which essentially means that it's to do with the imperfections of the data set you are actually able to collect. Okay, so if you do collect some more data, perhaps the data set will be better, and multicollinearity will not be as much of a problem. So the idea here is acquiring more data, either increasing the sample size or including additional variables, can reduce the severity of the multicollinearity problem. But alongside that, it's not always the case that this is practical to do. For instance, if you've got a time-limited project like a dissertation, you might just be able to collect the data you've got and that's it. Okay, so I think this reflects that multicollinearity is always a sample feature and is always a reflection to some extent of the fact that the data set that you have collected will have some imperfections in it. Okay, and the idea would be that if you increase the sample size, you can increase the range of values that the variables take, and so you can hopefully reduce the problem of multicollinearity. So another option is to just rethink the model, and I think the major thing to take home from this, if you're going to study a MSc dissertation, is to try and make sure as much as possible that the steps you undertake in the analysis are linked to previous published research. So it says here that sometimes a model chosen for empirical analysis is not carefully thought out, and I suspect the way of resolving this probably requires a deeper level of thinking than we can possibly teach properly on this course. But some common examples of mistakes that you might have in the original formulation of the model might include omitting some important variables or not getting the right functional form of the model. Beyond that, it's possible that you might get more joy using more advanced statistical techniques. So possible examples include factor analysis, principal components analysis, and ridge regression. Now again, it's rather hard to include everything that you might need on an introductory course like this. Just remember that statistics is a big area and there's lots of possible different ways of undertaking an analysis. Okay, but there is real value in studying these regression type approaches first, precisely because they've got such broad application within accounting and finance. So multicollinearity really has two roots. Firstly, it's to do with the imperfection in the data set that you've got available. Secondly, it's a computational numerical problem, and it's a problem in the sense that your laptop isn't going to explode, but you may not be able to trust computer generated model output and take any results that you get at face value. Now alongside that, another important numerical problem is this thing called micronumerosity. The argument is that multicollinearity has arguably received excessive attention in the literature. In contrast, micronumerosity refers to the smallness of the sample size, and it's thought to be some as at least as important as multicollinearity. Okay, so if you're concerned about the small sample size, then the natural thing to do is try and collect more data. But as I said before, with a time-limited project like dissertations, there may be strict limits as to what's ultimately possible. There's no right answers here and no substitute for common sense and critical thinking. I think that both multicollinearity and micronumerosity are inherently due to imperfections in the data that you've got available, and there may be a limited amount of things that you can do in order to counteract that, especially if you've got limited time available. So I wanted to try and illustrate stepwise regression approaches by going back to this Longley data. So it's a data set that's been so famous it's actually got a name. And I wanted here to try and present the stepwise regression approaches that represent as close as we can get to an objective way of approaching messy problems. Okay, so in terms of this Longley data set then, you want to try and explain the number employed in terms of these things here: the gross national product, the number of unemployed people, the number of people in the armed services, the non-institutionalised population over the age of 14, and the time trend in years. Now, as I said before, when you're bearing this problem of multicollinearity in mind, the thing to watch for here is high R squared values and low t values. So indeed, if you fit the full model with all these x variables in it, you get precisely this thing here, high R squared values and low t values, which is the indication that you've got a problem with multicollinearity. This makes sense from the wider context because you naturally expect that there are going to be interrelationships between these different x variables, so a certain amount of redundancy in the model, hard to isolate the individual impact of these x variables upon the y variables. And the idea is that if you use a stepwise regression approach, it's methodical and relatively objective. So as you said before then, so similar commands for reading in the data should work the same way every time. So the data is in the file longley.txt, available from the module page on campus. So the best way to do this is to save this .txt file onto a USB stick, and then once you open R up, you need this read.table command, and you then need the file path to match the letter of the USB stick. So when I did this on my computer, my USB was drive E, so you need an E as the first bit of this read.table command. If your USB drive is called something different, you'll need a different letter in this first bit of the read.table command. Then everything else should have the same rhyme and rhythm as you've got before. So how to read this? So we're calling the thing longly, and then when you're looking at the R commands from x2, x3, x4 all the way down to y, the name longly has to match the thing that you call the object identified by the read.table command, and then x2 is just reading off the first column of this data set, x3 is just reading off the second column, x4 is just reading off the third column, x5 reading off the fourth column, x6 reading off the fifth column, and y is just the final sixth column. Okay, same rhyme and rhythm to the R code every time that you do it. There are three basic approaches within stepwise regression, and probably the best one to go with is stepwise selection. Okay, but within this there are sort of two different flavors. So the first possibility is to start with forward selection. So you start with the basic model just equal to term, essentially add successive terms until no more of the x variables are statistically significant. The alternative is backward selection, so you start with the full model with all the variables included, and what you do is try and delete terms until all the variables remaining in the model are statistically significant. And then the stepwise approach, which is probably the most advanced approach of all three methods, is a sort of hybrid of the previous two methods. So you start with the basic model with just a constant term in the model and add successive terms until no more terms that you add are statistically significant. However, each time a variable enters the model, a backward regression deletion step is performed to check that all the variables included in the model are still significant throughout. Okay, so stepwise selection includes forwards and backwards movements, and it's therefore more advanced because there might be some blind spots and complicated problems with both the forward selection method and the backward selection method. How the stepwise regression works in R then, so you begin by fitting the full regression model, and you need to call it something. Here I've just called it a.linear model, and remember the R code every time is the same rhyme and rhythm, so this is just the linear model where the y variable relates to these variables here, x2 plus x3 plus x4 plus x5 plus x6. The x variables, you have to have a plus sign linking them all together. Then you need to fit the null model with just the intercept term and call it something logical. Here I've just called it null.lm, and this is just a linear model where the y variable depends on just a constant term. And then there are, as we discussed before, essentially two basic differences depending on whether you're doing forward selection or stepwise regression, where you have to start with a null model, hence the need for definite labeling of these regression models above. And then the alternative is backward selection, where you start with the full model, hence why you need the a.lm above, because you need to identify what the full model is, and you may also need the null.lm model just to identify what the minimal model is. Okay, so both these methods actually need the full model I should say, and the null model, and these need to be defined as above the R code, given a sensible name.